Hello, welcome to lesson 21 on sums of random variables. First, we're going to look at the uniform distribution. In the discrete case, take the example of rolling a single die and looking at its face value. And we see here that the probability is the same for each outcome, 1 through 6. The probability is 1 out of 6. Now, if we look at the probability mass function for rolling a pair of dice and recording the sum, this is the sum of two uniform random variables, independent. And we see that the shape here is triangular. The most likely outcome here is a 7, and it trails off as we go farther away. It's only one way to get a sum of 2, 1 and 1. Only one way to get a sum of 12, 6 and 6. So we see here that the sum of two uniform random variables has a different shape. It's no longer uniform. In this case, it's triangular. So triangular shape here. All right, so one technique for finding the PMF of a sum of variables is to compute what's called the convolution. So we'll take a look at that. If we look at two independent discrete random variables, x and y, each has its own probability mass function, PMF, and z is the sum, x plus y. We want to find the PMF of z. We can call that h. So to calculate this, to determine the probability that z takes on a specific value, suppose x is equal to k, then y has to be z minus k for that sum of x plus y to give us this value z. So once x is k, y has to be the total minus k. And so again, assuming these are independent here, we can do the probability by taking the product of x equals k times the product of y equals z minus k. And so this calculation can be used to construct the PMF, probability mass function of the sum. And this process here, this product, the sum of this product situation is the convolution of the original. It's the convolution of the original PMF probability mass functions, f with g, the PMF of x and the PMF of y. And so we can run through all the values here that z can take on by looking at the sum of f of k times g of I minus k. So the PMF, probability mass function of the sum of two independent random variables, is going to be the convolution of the individual PMFs, f star g. In the continuous case, it's essentially the same exact thing, except we're integrating. It's the same kind of product situation, working with the density of x, density of y, to arrive at the density of z, which is the sum. And again, it's the convolution. It's the convolution again. All right, we'll look at an example here. Now we're going to take a look at the uniform situation, this time continuous, on the interval 0, 1. On the interval 0, 1, each density is a constant 1 when the variable's between 0 and 1, and it's 0 otherwise. So we're going to look at the density of the sum z equals x plus y. We're going to do the convolution. Okay, so it's the convolution here, density of x times density of y evaluated at z minus x. Now this gets a little bit tricky. The density of x, this first expression here, this is going to be 0 unless x is between 0 and 1, and then the value is 1. The second part is a little bit trickier. The expression, the density, is only ever 0 or 1. It's 1 when the input, when the argument is between 0 and 1. So we need z minus x to be between 0 and 1. When that occurs, we will have a value of 1. Otherwise, this density is 0. All right, so with the restriction here that it's only going to be non-zero when z minus x is between 0 and 1, and we can isolate x here by subtracting z in each expression, multiply by -1, reverse the arrows, x is going to be between z and z minus 1. Now we have to do a few cases here because the sum of x plus y could reach as high as 2. X is between 0 and 1, y is between 0 and 1. The sum could be anywhere from 0 to 2. So you have to do a couple of cases here. If z is between 0 and 1, then what happens is that x can range from 0 up to z. Remember that z is equal to x plus y, or we could write this as x is equal to z minus y. So x can never be larger than z. We can also see that here. X is less than or equal to z. Now, the next case is where z is between 1 and 2. Now, if z is between 1 and 2, x can't be extremely small. So we're going to have a variable limit there on the lower bound here. X is going to be between z minus 1, and then the largest that x can be, x cannot exceed 1. X cannot exceed 1. Another way to look at this here is that the largest that y can be is 1. So the smallest that x can be is z minus 1. And the largest x can be is 1. All right, so coming back to the integration here, when you integrate 1 dx, you just get x, so you just get the difference of limits, which is upper minus lower, z minus 0. If you're integrating from z minus 1 to 1, you're going to get 1 minus z minus 1, which is 1 minus z plus 1, which is 2 minus z. And z cannot be negative or greater than 2. It's x plus y. Each is between 0 and 1. So this is the only situation we have to look at here. And we have that this expression, this density of the sum, is equal to z when z is between 0 and 1, and it's equal to 2 minus z when z is between 1 and 2. If you wanted to see the cumulative distribution function here for the sum, you would integrate each piece. The integral of z is z squared over 2. The integral of 2 minus z is 2z minus z squared over 2. Now, there is an extra constant here. I'm going to let you fill this in. But remember that we're dealing with a running total here. The CDF is a running total, the cumulative distribution function. So any value, when you're plugging in a value into these expressions, you're supposed to be getting the probability that it's the running total cumulative probability of z less than or equal to that expression. So that's why we have to um, put in that certain constant of integration there to get that to line up with the cumulative running total. So what does this density look like? So the original expression here, each one individually, was on 0, 1 with a constant distribution. This case here, it's a height of 1. Now the density of the sum, it's going to be triangular, as we saw in the discrete case. We have the z portion here from 0 to 1, and then we have the 2 minus z portion, which represents a slope of -1. And so, again, we see a triangular situation here when we add two independent, uniform, continuous random variables. So the sum of two uniform random variables is not uniform. And the cases we've seen, it's triangular shape. So another question here to think about, why does it make sense that if you're adding two uniform random variables, independent from 0 to 1, each between 0 and 1, why does it make sense that it's going to be more likely to get a sum closer to 1 than it is to get a sum that's closer to 0 or 2? All right, continuing on here, we're going to look at one more example here. The calculations do get a little bit tedious. The algebra gets a little bit messy. The result is the main point here. If you take two independent normal random variables and you sum them, you will still get a normal random variable. In this special case, if each one has mean 0 and variance 1, the sum will have mean 0 and variance of 2. Now, in this special case here, where each one is mean 0, variance 1, we get a simplified density function here, 1 over root 2 pi e to the minus x squared over 2. And so that's going to be both x and y have that density. So plugging into the convolution formula here, we're working with the z minus x situation. So we have 1 over root 2 pi appears both times. We have e to the minus x squared over 2 and e to the minus z minus x squared over 2. Multiplying the e terms together, you're adding exponents. They're both negative. We do a factoring here and multiplying out. And then eventually we do completing the square in x here. We're completing the square. Excuse me. Yeah, we're completing the square in x, and it amounts to adding and subtracting half the middle coefficient. So we're adding and subtracting half the middle coefficient squared. So we're negative z over 2 squared. That's where the z squared over 4 comes from. And so we're adding and subtracting that expression. Then we can factor out this e to the minus z squared over 4. That can be pulled out of the integral here. And then again, some more substitution, some more manipulation. We end up essentially with getting back the normal density, which has to integrate to one whole. It's one of the definitions of a density. It has to be greater than or equal to 0, and the integral minus infinity to infinity has to be 1. So multiplying through by root 2 pi, we see that this integral here, minus infinity to infinity e to the negative z squared over 2 dz is equal to root 2 pi. So with a little bit of manipulation here, a little bit of a substitution, we can get an expression for this integral here where the exponent on e is just negative u squared without the 2 on the bottom. And when we do that, we get radical pi instead of radical 2 pi. And so then substituting that in and reducing down, we finally arrive at the result here, which is that the density for the sum is 1 over 2 root pi e to the minus z squared over 4. Now, matching that up with the general normal distribution density, we see here that the standard deviation, if we look at could get this from either denominator. If we look at this denominator here, we see that the sigma expression needed to be a root 2 to get root 2 times root 2 is 2. So the standard deviation is going to be root 2. Now the mean is still 0. There's no shift here in this expression in the numerator. Can also solve for sigma in the fraction in the exponent of e. We have 2 sigma squared is 4. So sigma squared is 2, and sigma will be radical 2. So in general, what's the takeaway? If you start with a normal random variable x, mean mu1, variance sigma 1 squared, and y also normal, mean mu2, variance sigma 2 squared, and x and y are independent, then the sum is normal. So different from the uniform case. The sum of two independent normal random variables is normal. The mean is the sum of the means from the expected value of x plus y. So the mean is mu1 plus mu2. The variance, again, for when independent, then the variance is additive. It's sigma 1 squared plus sigma 2 squared, which in this case would have been 1 plus 1 is 2. And then the standard deviation is the square root of that sum. It's not quite additive. It's not just sigma 1 plus sigma 2. You have to work with the variance first, sum those squares up, then take the root to get the standard deviation of the sum. In this case, it's root of 1 plus 1, which is radical 2. So again, the result is the main focus here. You add two normal random variables independent. The sum is normal. The new mean is the sum of the means. New variance is the sum of the variances. Standard deviation, square root of the variance. And it does turn out that the average of two normal independent variables will be normal as well. And here's a reference to some of the work on convolution here. Okay, this wraps up lesson 21. As always, please don't hesitate to email or ask questions in the discussion board.